So think back 10 to 15 years ago. You probably had a big, bulky TV in your house, didn't have a great picture, but it was your TV, and it was awesome because you could watch television on it. Then all of a sudden, nice, fancy HD TVs started coming out. They were thin, they had really great pictures, and football looked awesome on them. So all of a sudden, you really wanted this nice HD television. And all the research was making a nicer television, lighter television, thinner television. Well, my research in the field of photoacoustic microscopy is along the same design, trying to improve the resolution of our images so we can get nicer images, better images, and also making our microscope smaller and more easy to use, more compact, so it's more portable around different places we can do research. So on the right, you can see the kind of images we used to get from photoacoustic microscopy. You can't really tell what it is, it's kind of blurry, but if you know what you're looking at, you can figure it out. On our left, this is our first stepping stone in our research, where we went from this low-resolution, low-quality TV to a nice high-definition image of actually red blood cells. Red blood cells are very small, about 10 microns, which is about a little bit more narrow than your fingernail, a lot more narrow than your fingernail, so very small. And we can actually see the whole red blood cell in the image. So this is a large step forward. This is the first time anyone had ever used photoacoustic imaging to capture a full image of a red blood cell. But we wanted to go farther than that. We actually want to image the mitochondria, which is the powerhouse of the cell. So the mitochondria is very, very small. It's about a tenth of the size of a red blood cell. So the question is, why do we want to image the mitochondria? If it's so small, are we just trying to make a nice high-resolution image? Or do we actually care about what we're imaging? Actually, we really are interested in mitochondria for a different reason other than it's small. In addition to being able to see small things, we can look at whether or not they're being activated, so whether or not red blood cells are carrying oxygen, or whether or not the mitochondria is actually doing an active process. So if we can actually see if the mitochondria is making energy in a cell, we can determine the health of that cell, and we can actually determine how that cell is going to react to different drugs. So this will actually help us guide drug design, and especially for cancer treatments where the mitochondria is a very important part of the cell. So we hope to leverage what we've learned from making this high-definition television of red blood cells and going on to the even brand new, fancier, super high-definition televisions that are starting to come out now, and actually imaging the mitochondria so we can guide future development of drugs for cancer therapies. Thank you for your time.